and the zone file has some header. This is the start of authority record that indicates, that tells which zone this name server, the name server with this file, is responsible for. And then it has a set of records. Most of them are address records. These address records, very simply, they just associate a name with an IP address. And that's what they look at taking place. So that's essentially if a new host is created and has a name, at some name server, there is a resource record for this. Relatively simple. So the way to read it here is mylab.com, and here's the period.com. Yeah? This is the fully qualified domain name of this kind of describing the zone that is handled by this name server. It says startup authority is pc4mylab.com. So this one, pc4 in mylab.com, that is the name server for the domain mylab.com. Simple enough. Then there is some more information here. I think this is an email address. Hostname at mylab.com. I think this should be an at or something. Or this is a period, but should be, yes, this is written as a period, but should be interpreted as an at symbol. This is essentially the email to contact, the contact information of somebody who's responsible for this. There is some information about the information about expiration, time to live of cache records. I don't describe it here. Then there is a record here for the name server, pc4mylab.com. And then there's just the whole list of address records. Yeah, it's saying pc4mylab.com is at 10.01.41, pc3mylab.com at 10.01.31, and so forth. What is not in here is a delegation of a domain to another name server. The delegation would also be an entry here. For some reason here I don't have this on the slide. And that's the hierarchy. That's essentially the configuration of the zone files sets up. What you can also have is there are entries for the MX entries for mail servers, and the special entries for mail servers, and so forth. All right, that's the resource record. Now let's talk about how a query works. We went over it roughly last time. Let me just recall it. So what we have is this is a client, any regular computer that is using the DNS. An application, there is a common component that serves as the client of DNS for all DNS interactions that happen at this host. And this one is just a regular computer. So if there's an application program that tries to make a web access to neon.ecplab.edu, it makes a request to the local client that's called the resolver. The resolver is then responsible for returning the IP address. What the resolver does, it contacts name servers. It contacts the configured. If you configure a name server, on a host, that is the name server, the host that has been contacted for resolving most IP addresses, for resolving most DNS queries. So 3 steps. Resolver resolves, returns the IP address, which then is passed on to the application program, and from then on, the application program has the IP address, and then TCP, any transfer protocol, and then goes over. Now, there are 2 types of queries that DNS allows. The names are not very well chosen. that sounds like there's a big difference. There is a recursive query and an iterative query. An iterative query is so the issue with the recursive query is that the let's just have a picture. It's kind of easy to see on the picture. On the recursive query, what is happening is that a resolver asks the name server, and then the name server is responsible for resolving the entire query. Let's look at the difference here to the iterative query. In the iterative query, the resolver asks the local name server. The local name server then comes back with the closest authoritative name server, and then in most cases returns a root server. And from then on, the resolver is responsible for making the resolution. That's essentially the difference. Yeah, this is iterative and this is recursive. It's kind of recursion is kind of why is it called recursive? It is from the perspective of the resolver. Just ask the query and get the response back. What recursive somehow implies, the name implies, that the name server asks the root server, which then in turn asks the top level domain, subdomain server, and then the query goes back in a recursive fashion. That is not the case. Do you see what I'm saying here? Yeah, that's a kind of the name is just not very well chosen. It would kind of, what would real recursion be? Resolver asks for www.microsoft.com, goes to its local name server, and the name server goes to the root server. The root server passes the query onto the .com server, which passes it onto the Microsoft.com server, which then passes it back to the .com server, passes it back to the root server, returns it to the name server, which then returns it to the client. That's what we understand as a recursion. That is not what takes place, and it makes sense that it's not done in this way because the root servers would just have to cache all pending queries. It's not done. Yeah? So the contact with the DNS servers, the contact of the DNS servers in the hierarchy, with the exception of the local server, the configured server, name server, and this is also a name server. Yeah? It's the local name server. The interaction is, with the exception of the local name server that is contacted by the resolver, is just give me, I look for neon.ts.toronto, so it returns to, okay, I give you the name server of .edu, which this root server has by looking up the delegation is in the zone file. It's coming from the zone file, returns it. Then the name server says, okay, give me neon.ts.toronto edu. Then the edu server then comes back and says, okay, here's the name of the Toronto server. Then the name server goes and says, give me neon.toronto.edu. It comes back with a referral to the CS Toronto edu server. And the query is sent to the CS Toronto edu server, which then provides the IP address of neon, which is then returned. You're with me? So you're looking here at the iterative query. The iterative query just returns a referral to, in most cases, kind of the standard case, the root server. If the name server has more information, it provides also the closest server that it has available. Yeah? So, and then for the iterative queries, the resolver has to do the iteration and perform it. But the queries that the resolver has performed in an iterative query is these are the same queries that the name server would issue. So how does the name server, both queries are allowed. In most cases, what we find is that the name server is responsible that you have only, that you run recursive queries. So that's the most cases, and I don't talk here about, we do not really talk about the packet format of the DNS. Maybe we should. It's not terribly interesting. This is a flag being set that the query is being issued. A packet with a query, there's a flag that indicates whether the query is it's an iterative one or a recursive. All right. So let's now look at this and then now better understand what's going on. So with the recursive query, the resolver must, the server must resolve the query. When the name of this cannot resolve the query, the server issues a query to some other server. Yeah, that's what we saw. The name server goes to root edu, Toronto edu, CS Toronto edu. For the iterative query, the server returns the best possible answer, which is the correct answer, or it refers to another server. If you're having something, if you are having a local request, that's then something out of the zone file, that is then being sent. If there's not an exact match, it sends a referral to the resolver, or further specifies another name server. Root servers and top-level domain servers only handle iterative queries. Yeah, so this is essentially the query that is sent here is the same nature of the query over here. If you now make this query recursive to the root server, then the root server would have to perform the function of the name server. So it continues. Yeah? So here we have the, if all queries here would be set, let's put it like this way. This query is set as a recursive query. So the name server must provide the IP address. The name server issues a query. If this query was also set as recursive, then the root server would be responsible for making, resolving the IP address. So what we have here is that the request to the root server and the following queries, they're all iterative. So with me here, yeah? For the iterative queries we have this. So we first contact the local name server, the configured name server. From there on, you get a reply. If it has the IP address, the name server knows the IP address, it provides it. Otherwise, it returns with the name server and then you resolve it. Let's see, that's pretty much, caching, very important. So servers are allowed to cache information if information is if this name server has resolved the query, this server here, if this one here is the name server 128.100.100.128, the U of T name server, it sees a lot of queries. Just collects a lot of information. It uses this, it can use this information. It can use this information and they will cache it locally. So if a query comes to somebody at www.microsoft.com, most likely that request was made in the last 3 minutes by somebody at U of T. So in this case, the reply that comes back, the name server, there was a previous query for the same name and it has the IP address, the name server then sends it from its local cache. Yeah? But if it sends something from a cache, then the reply is being labeled as unauthoritative. And we saw that yesterday. Yeah, when we did the query for some name. Let's see, maybe we can look at this now again, let me understand what's going on. So let's look at, what is the command? And program. On Unix systems, so on Unix systems, now host is the name because NSLookup is I think they deprecated. NSLookup. Let's try www.microsoft.com. So we're getting this back, and what comes back is a non-authoritative answer. You see the server is 128. That's the configuration server. We contacted it. Then the non-authoritative answer comes back, and it is LD1WW MS Microsoft Akamai DNS, probably stands for Akamai, the Content Service Provider .net, and it provides the address. And these are the set of, it also provides aliases. Aliases are other names under which this IP address is being mapped to. And you can have multiple names mapped to the same address. That's called an alias. Let's see if we can get something. Let's get maybe something that. Does somebody know? 100.11.1. Okay, so that one, you see here, this reply, let's see, server, a non-existing domain, cancel. Okay. No, we got the reply back at both cases. Yeah, this is can't find server name. I don't know what that means. So the server that replied came back with Tesla.com.ca, which turns out to be the mail server of the communications group in the ECE department. Bad convention, that one is the name server. Yeah, we would not do it. I found this very. Anyway, that's what I did. But this is an authoritative reply. Yeah, because the name server is configured with it, it knows. All right. Is there anything else? Any questions on the? I think that's all I have on DNS. Do you have any questions? You'll go through this, yes?
So did you say unauthoritative means it is in the cache and it doesn't actually make the query?
It does not make it clear. That's right. If an entry is coming from the reply from the server, it's coming from the cache, it's not authoritative. I believe what can happen is that a query can be issued that the client wants to have an authoritative reply. In this case, then the server has to go out. But regular requests are coming out that the cache reply is okay. So you know, that's what is done. What I can do is, let's see, I have a few things. I have this maybe I can go back to this slide of set of the internet. I can find something. Few minutes about just some things that are interesting about the internet that we have never talked about. All right. Internet. So this is the lecture that was listed for last week. Just a few things to know, yeah? So what defines the internet? That's an interesting question. Define the internet. You use IP. What else? It must somehow draw from the public IP space. So using the internet is running the internet protocols. If you're running IP protocols down in the lab, we're not connected to the internet. So even though we're running IP, we're not connected to the internet. So what's also part of the internet is that we're using the global public IP address space of the public IP. We're running TCP and we're providing kind of the end-to-end delivery of service. Now it turns out that there is a definition of the internet that was done in 1995 by this is called the FNC Federal Networking Council. This is a subcommittee of the Regulatory Commission for Communications. So they said that the following language reflects our definition of the term internet. Internet refers to the global information system that logically linked together by a globally unique address space. That's important, the globally unique address space. That is based on the IP protocol and its follow-ups. If it's successful, it's able to support communications using the TCP IP protocol suite. So that's the protocol stack that we're working on. It doesn't refer to IP and TCP per se. It includes UDP, it includes ARP, it includes the routing protocol, it includes DNS, all the services that are part of the protocol stack. And it makes accessible public or privately high-level services layered on the communication and related infrastructure described here. So it's interesting. The applications running on this infrastructure here of IP protocol and a common address space, the applications are part of the internet. I'm not sure that that is very interesting. It's just somebody asked me to define the internet. There is a definition. Yeah? Let's see. Growth of the internet. This is actually a little bit. It depends what you're interested in. If you're trying to be timely, and I'm trying to be timely here, this is the latest information that is available. So currently, there are roughly 900 million hosts on the internet. What is actually most interesting is to see a log curve, and I used to have a log curve of this, but I deleted it. Let me maybe go to something else. Let me just give me 1 second here. I just need to make a quick search. Let's just search here. This is the more interesting slide here. Let me just turn it back on. This is a log scale of this plot. It's not the same plot. It ends here in 2001. So at 2001, you're roughly there at, these are 10 million only. 100 million hosts. Yeah, 100 million hosts were reached there. So what you find is, if you're looking here at the log scale, you're going from August 81, since we have 200 hosts. That's when the IP address space was created. Let's look at when was DNS created. DNS, we said, was written in 1985. 1985. We had 1,000 hosts. Yeah. In this period of time, you have this .hosts file. where each computer had a complete list of all computers on the internet. With 1,000 hosts, people switched over. Let's look at some other landmarks. The landmarks of CIDR, introduction of CIDR. CIDR was introduced in 1993. You see, there were, at that time, roughly 1 million hosts on the internet. 1 million, yeah? So now, what are the landmarks that we find date-wise? The introduction of the web. Yeah, the web, HTTP came about pretty much 92, 93, also in this time frame here. Yeah. So this was here. Interesting to see this. This period here was the time of the kind of this internet bubble when the internet took off. 1995, that's when the internet became commercialized. 1995, maybe 5 million hosts. So, taking over in 1994, this is what we have on the other picture here. 1994 is over here. 1994 is now where this other picture started here. 1994 is this. Just to get a sense of the orders of what it means, orders of magnitude of growth. So what you see in this picture here, and that growth is, so what you see here is that it's taken from 81 to 85, the order of magnitude. Then the next breakthrough here is from 84 to 86, an order of magnitude. Here we're going from roughly 87 to 89, another order of magnitude. 89 until 92, 3 orders, order of magnitude. 92 till 90, roughly 96. That's the generous here, maybe again in 3 years, an order of magnitude. Then we're here from 95 until 2005 years, an order of magnitude. In 5 years, yes, actually the logarithmic growth has slowed down. Yeah, so here we're going from, let's see, where was 90? We were here at 100 million. 100 million now, 10 years later, an order of magnitude. Yeah, so if you have the growth curve here, looks a little bit dramatic. This one is in fact the more dramatic curve, because you have over the periods of time until 2000, essentially every 3 years, a new order of magnitude. Yeah? But you know, as with all logarithmic growth schemes, it has to come to an end, because at this time you cannot make another order of magnitude. Well, you can. You can. That would be maybe one more or 2 more. But then it is pretty much coverage of IP devices worldwide. I thought this was interesting. All right, let's leave it here. So the thought this was kind of to provide some bit of information. Is this interesting? Yeah, sorry. Very good. See you then tomorrow. So what we're doing starting tomorrow is talk about IP multicast. That is technically a little bit challenging. Again, there should be a laser lab associated with it, which we are doing. That would be a very, very difficult lab.